Okay, so today we'll discuss about 1D flows. Hmm? So what are 1D flows? So that's the idea. So remember that what was one-dimensional? Sorry, what was one-dimensional maps? What were one-dimensional maps about? So you can see maybe what I can do is I will switch in between two slides. So here we will write about 1D discrete maps, what we know already, right? And here I will write about 1D flows. All right. So we'll see the difference between them. Okay. So let's begin by recapitulating whatever we have learned so far. So first, what we learned in 1D maps, like we learned about fixed points, right? So suppose you have a one-dimensional map like xn plus 1 is f of xn, right? Where f is the rule associated with the dynamical system. Then what is the definition of fixed point? Huh? Is equal to the same, right? So that is like a fixed point is x star such that it satisfies f of x star equals to f of x star, right? I mean, you have a point, you apply the map, still you will be at the same point again. So it doesn't change. Even after applying the f and again, it doesn't change. The point doesn't change, right? So after understanding the fixed point, how we and what we understood next is about the stability of a fixed point, right? So stability, like when a fixed point is stable if the derivative, absolute derivative of f at the fixed point is less than 1, right? If it is greater than 1, absolute value is greater than 1, it's unstable, right? So this is stable fixed point, stable. What we understood next is like, what we understood next, anyone? We understood periodic orbits, like periodic orbits. That one-dimensional maps can also show periodic orbits. That means you have a point x0, you apply the map f, you go to x1, you apply the map f again, you go to x2, and if you apply again the map f, it will come back to the same point x0, right? So what does it mean? If you apply 2 times of x0, you will return to x0 again. If you start applying 2 times f0, you will go, sorry, 3 times f0, you will go to x0 again, right? So it's a period 3 orbit. It's a period 3 orbit. So it's a period 3 orbit. We also understood that I showed you in Python code that logistic map. We simulated logistic map bifurcation diagram, okay? And the logistic map bifurcation diagram, we saw chaos, right? So we saw chaos. That is period doubling route to chaos. Period doubling route to chaos, isn't it? Do you remember the bifurcation diagram I showed you? Period doubling route to chaos. How was the diagram about? Like, I hope you remember something like this. This was X, this was R. There was a fixed point, okay, like this. And then it bifurcated into a period 2 orbit. And again, bifurcated, doubled again. And then went to chaotic type dynamics. I hope you remember this structure. Yes. So this was chaos. This part was chaos, right? So period doubling route to chaos. 1, then 2, then 4, then 8, 16, so on to it went to chaos. So period doubling cascade to chaos. Now let us we will learn in this class about one-dimensional maps. That is our aim today. Okay, we will learn about one-dimensional maps. So let us see how the definition changes here. So here we will not call them fixed points for 1D flows. Okay. Now what are 1D flows? Okay, that's the question. So we'll start with next slide, and whenever we find a property, we'll come back again and write it so that you can know the difference between a one-dimensional map and a one-dimensional flow. Okay. So let us come back. So one-dimensional flow. So 1D flows is something like x dot equals to f of x, right? Now what is x dot? X dot is nothing but the derivative. dx by dt equals to f of x. Okay. So it tells you the rate of change of x is equals to f of x. Okay, the rate of change, how x is changing? X is changing with respect to time as f of x. Okay, So, but one thing is here is that x changes with time continuously. But previously in the discrete map, x was changing in a discrete way. Okay. So due to that same property, because here x is changing in a continuous pattern, we see lot of new features. Okay. But since x is changing continuously, we also have some limitations. Okay. We also have some limitations. So let us see what each of these mean to our case. Okay. So this modeling tool we use for flows is differential equation. So this is a differential equation, right? Okay. So basically, in continuous system, you have something like this. Like there might be two variables x dot and x. Then here you start from here also you have an initial condition x naught. Okay, you start from a point. You will always start from a point. So this x naught, I hope you remember initial value problems. You have a differential equation and it is given. You start from an initial condition, right? So you suppose you started from initial. What is x naught? So x at time t equal to 0 is equal to x naught, right? X at time t equal to 0 is x naught. So this is known as an initial condition. So once you start from an initial condition and you monitor this 1D flow, so it instead of moving discretely, it will move very continuous fashion. Okay, it will move in a continuous way. It will move in a continuous way, right? So to make a correct diagram, this is not a correct diagram. You will understand why, but maybe it will go like this. It will go like this. Okay, in a straight way. It cannot have oscillations. You will see for 1D flows, it cannot have oscillations. We'll understand why 1D flows cannot have oscillations. Okay. Okay. So this is the idea. Whereas for this is for 1D flow. Whereas for your what do you call the discrete map, you will have something like this. It will be like x naught you started with. Then you apply the map f. It might be x1. You apply the map f again. You go to x2. You go to x3, can come to x4. So you can see it is not a continuous jump. It is rather a discrete jump, discrete jumping of points. Okay. So this is 1D map. So you can see the contrasting feature in between those two. Okay. Here it moves continuously, right? Whereas here it moves discretely, discrete. Okay. So that's the difference between the 1D map and flow. So a lot of the possible cases exhibit 1D flows like acceleration, angular momentum of your pendulum or angular velocity. These all changes according to time in a continuous fashion. So therefore these variables, if you want to model, you have to resort to flows. You cannot model it through maps. Okay. So that's the idea. So you will see the 1D maps. 1D maps don't have, I mean, much freedom as compared to 1D. 1D flows don't have much freedom like 1D maps. Okay, in 1D maps they can move anywhere because they are discrete jumps. But in 1D flows they have a condition, right? Like what is the issue? They only have a real number line. I mean, points. Suppose you started from this x naught, they can only move either in one direction, right? Can they move in one direction and also come back in the next direction? Do you think? Can they move in this direction and come back? 1D flow. In 1D map, will have only points discretely, like moving. So in 1D flow, you cannot go in one direction and come back in the backward direction. Okay, you can either go this side or you can go this side, but not as a mix. I mean, you can, because there is only one x. There is only one x. If it was x and y, I mean, if you have x and y, like you can either like come like this, right? You can go like this. But if you have only x, then you can go either in one direction or to the left direction. It cannot go like this and come back. If it comes back like that, then it violates your uniqueness property. I hope you have learnt in your high school days about uniqueness of a solution of ODEs, right? When it is unique, if it is the f is continuous and differentiable, it will be unique, right? So if it goes back like this and comes back again, then at a particular time, this is a particular time, you will have two solutions. You will have two solutions. One is along this side, one is along this side, which is not possible. And they cannot intersect also. I mean, you might think why it cannot intersect. So if you think like the solution is going like this and coming back, suppose it went like this and comes back. Okay, is this possible? I mean, they intersect here, right? Is this possible? It is not possible. Why? Because at the point of intersection, at this point of intersection, here you have one tangent, I mean derivative vector here, and when it comes back again, you have another tangent vector here. So at the point of intersection, there are two solutions. So you are telling that at one point of time, there are two solutions. I mean, two directions one can go, which is not possible. Which is not possible. So therefore, you cannot have self intersections in 1D flows. Okay, neither in your 2D flows also. Okay, because at the point of intersection, you will see why you have to visualize. So this flows, when it comes, your visualization has started. Okay, so what it tells you that x dot equals to f of x means if it evolves like this, suppose if it evolves like this in straight line, that means at any point x, if you take a derivative, what does that mean? It means dx by dt at that point, right? And it should be along that line. So wherever the flow will be a trajectory, at any point you can take a tangent and it will tell you where it is going. The tangent direction will tell you where it is going. So that will be very much helpful today in today's class. Okay. Anyway, so 1D flows, one of the limitations is cannot exhibit chaos. So due to his restricted movement, it cannot exhibit chaos. Because you know chaos is very like a very sensitive to initial condition and very chaotic. I mean, you cannot predict the chaotic signals, right? So 1D map can show chaos, whereas this one cannot show chaos. Cannot show chaos. Limited movement, limited freedom to move. That means can either move right of real line or can move left of real line. Okay, it can either move right of the real line or can move left of the real line. I mean, that is simple, right? Because you have only x. It can move either to the positive side or negative side. It cannot move both ways. Okay, that's the because it is just one variable, one dimension. When you have two dimension, it can make oscillations and all those things. So cannot show chaos and even cannot oscillate also. Cannot show periodic orbits. Cannot show oscillations or periodic orbits. So if it cannot show oscillations and cannot show chaos, then what it can show? Okay, what it can show? So it can show, I mean, it can stay at one point, right? If it cannot show chaos or periodic orbits, what it can do? It can at least stay at one point fixed, right? So if it stays at one point fixed, that is the equivalent of fixed point. So when in 1D flows, we call the fixed point in a different name, that is equilibrium points. Equilibrium point. Okay. So what do you mean by an equilibrium point? That's the criteria we will study now. Equilibrium point. Equilibrium point of a 1D flow. Okay, of a 1D flow. So what we have, our 1D flow represents x dot, that is dx by dt, is equals to some f of x, right? Now what does that equilibrium point means? Equilibrium point means you are there. Even though time evolves, you are still there at the fixed point. So if I am there at the same point, what does it mean? It means the rate of change of x is 0. The rate of change of x is 0, right? You are there in the same point. So rate of change of x equal to 0 means x dot equal to 0. X dot equal to 0. If I, can you put x dot equal to 0 here? So an equilibrium point x star of a 1D flow, okay? 1 minute. Okay, so what is an, let us begin again. So what is an equilibrium point of a 1D flow? So an equilibrium point x star of a 1D flow is defined as something like where dx by dt will be 0, or that is f of x at x equals to x star is 0. That means nothing but f of x star equals to 0, right? I hope it is clear. Hmm? So if I give you a 1D flow, how to find the equilibrium point? You just set that equation to 0, right? So you see how the definition is different from the discrete. So let us come back to here. Equilibrium point x star such that f of x star equal to 0, right? So can you see the difference between definition 1 for a map and for a flow? The difference. I hope you can see the difference, right? One is x star equals to f of x star, another is f of x star equals to 0, right? So 1D flow, that is you have x dot equals to f of x. X dot equal to f of x, okay? So this is the plan. Fine. Now you know how to compute an equilibrium point of a 1D flow, right? So now what is the next usual step? Any idea? Hmm? Why? To check stability. I mean, after finding an equilibrium point, you have to check whether it is stable or unstable, right? So how to check whether it is stable or unstable? That's the plan, right? So let us visualize. Let us visualize. Suppose in 1D flow you have a real line. Only the dynamics will happen in a real line. Real line means you have 0 and here it is positive, negative, right? Here it is positive, negative, right? It can only move either left or right or stay at the same point like that, right? Only these dynamics it can show. So now the question is like, suppose your fixed point is here, x star. Hmm? Understood? Your fixed point is here, suppose. Now, how can we tell it is a stable fixed point? How can we tell is a stable fixed point? Stable fixed point is something, if you start nearby that point, you will come to that point, right? Are you understanding? To make even more understandable, I will give another example. You might have seen pendulum. You might have seen pendulum, right? So what it does, if you push it on this direction, release, what happens? It goes like this, comes back here, stays momentarily at this point, goes like this, comes like this, stays again, goes like this until after some iterations it will be here only. Okay. So after some iterations it will be here, right? Agree? Pendulum will always be in the same position, right? Why always it is in the same position? Because it is a stable equilibrium point. So whenever you disturb the pendulum, it after finite time it will come back to the stable fixed point. So the idea is if you start from any nearby point and your equilibrium point is stable, then the if you evolve it, it will come to the stable fixed point. And if it is unstable fixed point, what will happen? So if suppose this is a stable equilibrium point. Suppose this is a stable equilibrium point. Then if you start from this initial condition, suppose this is my x naught, then what will happen? It will go to this direction and converge. Suppose you started from this initial condition. Suppose you started from this initial condition x naught here. Then it will go to this direction and converge. Why? It will go to that direction because your fixed point is here. Your fixed point x star is there, right? Can it go from here, any direction here, and converge like this? Here also you will have parameter. But here we are just not there yet. We'll discuss that. But what I'm asking is, I'm giving you a notion of a stable equilibrium point. Then I will establish a condition that yes, this is the condition for a stable equilibrium point. Now my question is, you started from this pink initial condition, then you evolved your flow. Okay. then you saw that yes, it will go towards this direction too and converge towards the x star equilibrium point, right? Now, if you started from this x naught, it will converge towards this x star, right? Now, I am asking you, can you go from here and converge? Can you go here from here and converge? That's my question to you. Is it possible? Why? Yes, exactly. This is a 1D map, sorry, 1D flow. So you have only the x direction to evolve. You don't have a y direction. So it is not possible. Okay. So it can only happen in this number line. It can only happen in this number line. Okay. It can be negative or positive or stay there. These things only can happen. Cannot be chaotic. Cannot exhibit periodic orbits. Okay. So this is the definition of a stable equilibrium point. Now let us look into something like unstable equilibrium point. I mean, suppose you have a number line again. This is 0, and suppose this equilibrium point now is unstable. So this is an unstable equilibrium point. So this is an unstable equilibrium point. Okay. So now the idea is, if you started from one initial condition, suppose here, then what will happen? If you simulate your flow, 1D flow, then what happens is it will go away from that fixed point, away from the equilibrium point. If you started from here also, it will go away from the equilibrium point. Why? Because x star is unstable. Whatever you start near will get diverged. So that's the idea. So this same idea, sorry, we will use in our equations, okay, in our derivation. So here I wanted to derive, if you want. Otherwise, I will just can tell the condition. Do you want the derivation a bit? Do you want the derivation of how to reach to a condition for stable equilibrium point? Then I can show. If you don't want, I can just tell you the condition. It will just 5 minutes. Just 5 minutes, easy derivation, nothing else. So the same thing. So what is the idea? If you start from a perturbation and check the flow, it should come back, right? So that's the idea. Same idea we will use here. So what we do is something, the topic is known as linearization. Okay, linearization. So we use linearization technique to achieve this. Okay. So what we will do is we will examine the dynamics, close to the equilibrium point. Examine the dynamics close to the equilibrium point x star. Okay. So what we do is, suppose to do that, if you want to analyze something closer to the equilibrium point x star, then what you do, let x of t is equal to some equilibrium point is there, then you consider a perturbation term. You consider a perturbation term which is also time dependent. So this is like, if you perturb it, whether it goes away or comes back near to the fixed point, near to the equilibrium point, right? So if it comes back near to the equilibrium point, it is stable. If it goes away, it is unstable. So therefore, the whatever we told in verbal language, we are trying to illustrate using the formula. Okay. So of course, we will not consider a bigger perturbation. So some perturbation like which is less than 1. I mean tiny perturbation, tiny. Okay, tiny perturbation, right? So what will happen to this? That's my idea. So if x of t is x star plus eta t, my question to you is, what is dx by dt? What is dx by dt? Dx by dt is nothing but d by dt of, right? Now x star is an equilibrium point. So it's a number. X star is an equilibrium point. It will be there. So it's a number. So what's the derivative of it? Hmm? 0. Yes. So it is 0 plus d by dt of eta t, right? D by dt of eta t. Now what is d by dt of eta t? You can write eta dot. I mean x dot is dx by dt, so you can write d eta by dt is equal to eta dot, right? So what you got? You got x dot is nothing but eta dot. That means rate of change of your state variable x in 1D flow is nothing but rate of change of the perturbation. How much amount of perturbations you are giving, the rate of change of that perturbation is nothing but the rate of change of your variable. Okay. That is eta t. I mean, what we did is you had, see, the same thing. This is this. I mean, if you, other way of saying this example is something like this. I mean like, this is your fixed point x star, and you perturbed it. You perturbed it. That is, you perturbed it to here, x star plus eta t. Now the question is, with time as time evolves, whether this perturbation will go away from that fixed point or come back to that fixed point. That's what we are changing. That's what we are trying to understand here. Okay. And if it comes back to the point x star, then it is stable. So we, through this notation eta t, we will try to find a condition, and what condition, such that it will come back to x star, so that we can generalize a definition of a stable equilibrium point. Can you, so x dot equal to f of x. Now to compute equilibrium point, you do f of x star equal to 0. So you got x star, right? Now how will you understand if x star is stable or not? You cannot always see graphically, right? You cannot always see graphically, because there might be some complicated function, you might not see graphically everything. So you have to derive a condition under which a fixed point, under which an equilibrium point is stable or unstable, right? So how will you do that? So this is a formal way to do it, linearization. So what you do, you see what happens near the equilibrium point, isn't it? I mean, I don't know if you are getting the idea, but okay. So this is dx by dt, you got x dot equals to eta dot. Now you already know, so what is f of x? That's the question. Dx by dt equals to f of x. So what is x? X is x star plus eta t, right? Can we substitute that? So this is x star plus eta t. Now, does this give you some thoughts? What is going to happen next? If you know about Taylor series, how many of you know about Taylor series? Taylor series? Yeah. So what you do? If you know, so what is the beautiful thing about Taylor series? So the Taylor series tells you that if you know the value of a function at x, then that is only enough to compute value of the function at a tiny perturbation, that is x plus h. Do you agree with me? That means Taylor series tells you that you don't, if you know value of f of x, you don't need to know value of f of x plus h in advance. You can compute based on the knowledge of f of x. This is the sole idea of Taylor series, right? So now suppose you know this and you don't know this, right? Can you compute f of x plus h? Yes. How? You can expand Taylor series here towards h and centered around h, right? How? F of x plus h is nothing but f of x plus h times the derivative of x plus h square by 2 times the double derivative, and so on. You can carry on like an infinite series, right? So this is like an order of h cube, right? So that's a Taylor series. So you just need to know what is the value of h. So now you can always know the f of x. You can compute the derivative at x, right? All the things you can do. So just knowing the past value of f, you can find all future values of f. That's how powerful Taylor series is. Okay. So therefore you see Taylor series popping up everywhere. I mean, I hope in gradient calculations also Taylor series pops, okay, in between, because in all the situations you are trying to predict the next value, right? So same thing we'll be doing here, apply Taylor series. So this you can just think of as h, right? So what has happened, it will be, if you Taylor series expand, this will be h, so eta t times the derivative at x star, right, plus order of eta square. Does it matter? That's my question. You understood order of eta square, right? Now, does order of eta square matter? That's the question. I'd say it will not matter. Why? Because you have assumed already that eta term is less than 1. It's a tiny perturbation. So when you square it, it will become even tiny, right? If you take 0.01 and you square it, what is the square term? 10 to the power minus 4. So it became even more smaller than 0.01. So when you take a squared, it will be very much less than 1. So it won't matter in your calculations, right? So therefore you can neglect, right? I hope you understand. You can neglect this as mod of eta t is less than 1. So the eta square will be even smaller. So this is the only derivation you will see, means a bit more difficult in this course. I mean, but logical, very logical derivation. Okay. But can we do something more here? So what is f of x star? What is f of x star? X star is an equilibrium point. So f of x star will be 0. It's already proved here. F of x star equal to 0. X star is an equilibrium point. So it will be 0 plus eta t times f prime of x star plus, I mean, doesn't matter those terms, higher order terms. Okay. So till now it is clear. I don't know, it got stuck. So till now it is clear, is it? Now what should be our next step? What should be our next step? Anyone? I'll give you some time to think. I mean, see, derivative of f came as she was predicting that next step is computing derivative, right? So you can clearly see derivative is popping up. Eta t times f prime of x. Now, can you spot something like f of x is nothing but this? So after this, what? So I'll give you a few minutes to think. Because just after some steps, you can clearly say that, yes, this is the condition. So remember that f of x is nothing but x dot. We know x dot equal to f of x. But we also know from equation star that x dot is also equal to eta dot, right? So can we write this f of x as eta dot? Agree, right? So what we have? Eta dot equals to eta times t f prime of x, right? Agree. Agree. So now this is a very nice equation. Very, very important and nice equation. What does it tells you? It tells you the rate of change of perturbation here. The rate of change of perturbation. Can you see the left side is eta dot. Now the rate of change of perturbation will tell you whether the perturbation is coming towards the stable fixed point or moving away. Agree. So how will we know the perturbation is growing or decreasing, decaying down to 0? What we want the perturbation to be 0, right? If the perturbation is 0, what does it mean? Remember, you perturb from the equilibrium point. So if perturbation is 0, it means very close to the equilibrium point. If the perturbation is increasing, what does it mean? It is moving out of the equilibrium point, right? So you have to check whether the perturbation is increasing or decreasing, evolving or decaying. That's it. And who can tell you that? The derivative can tell you that. Yes, exactly. I mean, eta dot is increasing or decreasing. That's what you need to know, right? I hope you got the idea. Very, very, I mean, simple, intuitive, logical idea. If you think logically, you can get this. Okay. So now my question is, okay. So now my question is, if you have, suppose, let us say this is eta equal to r, eta equal to maybe or f prime x equals to r something. I mean, just to slow things down a bit. So we can say eta dot equals to r eta, right? Can you tell how this equation you can actually write what is eta from here? I mean, a very simple one dimensional differential equation, 1D differential equation. What you do, if you remember your class 12th, this is d eta by dt equals to r eta, right? So what you have, d eta by eta equals to r dt, right? Then you integrate on both sides, isn't it? So what you will get, this integral d eta by eta is nothing but log eta. This is r into t plus some constant c, integration constant, right? So from here, what you get, eta equals to e to the power rt, some constant c naught, right? Do you agree? Do you agree this? Agree, right? So what does it tell? The perturbation eta of t increases or varies exponential way, but all is depending on r, isn't it? Can you see this? So what? Sorry. Yeah. Are you able to understand this? I'll make it bigger for you. So what is eta t? Eta t is nothing but the perturbation, right? So the perturbation, what does it tell? Perturbation increases exponentially. Perturbation increases exponentially, right? Yes, exponential RT. But whether it is exponentially increasing or exponentially decreasing, on what it matters? R. R, but on what value of R? It matters regarding the sign of R. Is R is positive or R is negative? Is it eta t equals to c naught, some c naught e to the power 5t, or is it some c naught e to the power minus 6t? If it is e to the power 5t, what happens? It will increase exponentially because time is always positive. Time is always positive. So if you have c naught e to the power 5t, what happens? It will increase exponentially, right? Now consider the case, it will increase exponentially, so it's unstable. Your equilibrium point is unstable. Now, if you have c naught e to the power minus 60, what happens? As time increases more and more, it will converge towards zero. Now the perturbation is coming to zero, close to zero. What does it mean? It is very close to the equilibrium point. That means you have come back to the equilibrium point, which means your equilibrium point is stable. Can you see how beautiful the derivation is? I mean, fully packed with logical ideas. Okay. So therefore, but this is R. Your 5 is R, here R is minus 6. So what does it mean? So it tells us that if your R is greater than 0, then your X star is stable, right? If R is less than 0, it means your X star is unstable, right? Now what is R? What is R? R is nothing but yes, good idea. I made a mistake here. Yeah. So what's the plan? What should be? R is less than 0, it should be stable. R greater than 0, it is unstable, right? Now what is R? Remember here, R is nothing but f prime of x. R is nothing but f prime of x, right? Agree. So what does it mean? No, from here you can see I already marked R to be f prime of x, right? So R is nothing but f prime of x. So can you see that if f prime, the derivative, if the derivative of f at x star is greater than 0, then your equilibrium point is unstable, right? Now, if f prime of x star is less than 0, it means your fixed point or equilibrium point is stable. Can you see how we derived the condition? How nicely we derived the condition for the stability of your equilibrium point of 1D flows. Okay, I hope you can understand. So now different way of looking at this is if you have a vector field x dot equal to f of x means it will change continuously, right? So if it changes continuously at any point of your vector field, how it changes, at any point it has a tangent. And what is the tangent? Nothing but dx by dt. That is nothing but f of x. So you have to take the derivative and check, right? So we'll see that. So f prime of x greater than 0 means if your slope is positive, you can easily say that it will converge to the fixed point. Sorry, if your slope is negative, you can easily say, yeah, I mean r less than 0, it is stable, right? Yeah. Based on that, you can decide. Based on that. Okay. So let us see. Let us see. I will see this. We will see in real examples how to apply this, and you will be amazed that how it can increase your understanding. Okay, by visualizing. Okay. So now another question is, okay, I told you what happens if f prime x is less than 0. I told you what happens if f prime x is greater than 0. But what will happen if f prime x is equal to 0? Right? So this is another question might pop in your mind. What happens if f prime of x star is equal to 0? In this case, this idea of linearization will fail. So the idea of linearization fails. That means whatever we thought of, it will fail. I mean, whatever derivation we did, if f prime x is 0, it will fail. We need some more methods to do that. Okay. So if your f prime of x star is greater than 0 or less than 0, you can easily apply this method. But if it is equal to 0, you have to go inside some other sophisticated methods, which we won't be looking, but we will see what will happen graphically. Okay, we will see what happens graphically. Okay. So okay, now to do that, let us consider an example. Now it will be fully packed with visualizations, all visualizations. Can we work with 1D flows now? Simple 1D flows. Okay. So you remember, can I start with x dot equals to x square? Is it a 1D flow? It's a 1D flow. dx by dt is varying as x square, right? Now the question is how it will look like if I draw x dot versus x. How it will look like? How it will look like? Will it look like this? I mean, not drawn properly. It should be exactly symmetric. Okay, I mean, it should be exactly symmetric like this. So, isn't it? So this should be x dot equals to x square, no? Okay. Now, can we find equilibrium point? What is equilibrium point here? Can you see x dot equals to f of x? Here it is x square. So what is the definition of equilibrium point? It is an x star such that f of x star equal to 0. Now f of x star equal to 0 means x star square equal to 0. What does it tell you? X star equal to 0. X star equal to 0. So what is the where is 0? At the origin. This is the origin O. So here is the fixed point. Okay, let me mark it with a bigger circle. I will tell you the reason why I marked with a bigger circle. Okay. Now see, this is your derivative, this is your vector field, how it flows. Okay. Now at every point you can draw a tangent. You can draw a tangent, right? Here also at every point you can draw a tangent. And that will tell you, uh, so yeah, that will tell you where it is going, right? Is it clear? Is it clear? So can you tell me for x greater than 0, the derivative is positive, right? I mean, the tangent is positive. Tangent is nothing but the derivative. At any point, tangent is derivative, right? Now on the side, on this side, mark my cursor here. On this side, on the positive side of x-axis, what is the slope? Is it positive or negative? Positive. Why it is positive? Because it is making less than 90-degree angle. Okay, it is positive. Now, if it is positive, the trajectory should move close to the equilibrium point or away. Away, yes, because the derivative is increasing. F prime x is greater than 0. It should move away from the equilibrium point. That's what we saw, right? Derivative is positive means it will be unstable. Unstable. If it is unstable, it means it will go towards this side, right? Away from the equilibrium point too. I hope you are getting it. The logic is clear, right? Okay. Now let us start somewhere on the negative x-axis. That is points here, right? So if you start from here, what is the slope? Slope is negative. If the slope is negative, it should converge to the equilibrium point at the origin. So how it should look like if it is converging? Exactly, right? So what you see from here? What you see from here is if you start from the negative x-axis, you are converging to the fixed point. Okay, what I will denote is if it is stable, I will denote it with blue. And if it is unstable, I denote it with red. That's the color notation I will follow. Okay, so now tell me on the negative x-axis, it is being stable because it is going towards the equilibrium point, right? So this side is kind of positive, like stable. Agree, right? Agree. Okay. Now what happens on the positive x-axis? On the positive x-axis, it is going away from the fixed point, from the equilibrium point. So it should be unstable, that part. So that part I am marking it with red, right? I hope you are getting it. So this kind of structure is known as semi-stable, semi-stable equilibrium point. It is semi-stable equilibrium point. Okay, it is known as semi-stable equilibrium point. Now remember what is f of x here? F of x is x square, right? Now what is the derivative of x? 2x. Okay, what is the derivative at x star? That is derivative at 0. 2 times 0, that is 0. So we told you that when f prime x equal to 0, it fails. The idea of linearization fails. So this is an example where it fails. Okay, and when it fails, you see equilibrium point as semi-stable equilibrium point. Okay, so it is partly stable, partly unstable. If you approach from that side, it is being unstable. I mean, anyway, anyone approaching this side will be repelled. Anyone approaching here will be attracted towards the equilibrium. So that's how interesting this is. Okay. Now let us look into the other case. Okay. Maybe can we look into the other case? Like the second question is x dot is equal to minus x square. So how it will be looking like? You have x dot, you have x. So it should be downwards, right? If it is downward, it should look like this, right? I mean, it has to be more smooth. Okay. But anyway, it's fine. So can you tell me what will happen? So as you know, x dot equal to minus x square also equilibrium point is the origin. Equilibrium point is x star equal to 0. So let me draw a fixed point here, right? A point there, right? Now my question is, if you start anywhere on the positive x-axis side and take a slope, so where it will go? I mean, your slope will be something like this. So the slope is making an obtuse angle. That means your slope is negative. If your slope is negative, it should converge towards the equilibrium point. Towards the equilibrium point means it should converge like this, right? So if it is converging towards, that means it is stable. So I will mark this as blue color, right? Agree. Now let us look at some points which are coming here. I mean, on this side. So if you do, your tangent is something like this. Tangents, right? So the tangent is making an acute angle. That means less than 90 degree. So it should be, your slope should be positive. If your slope is positive or derivative is positive, it should move away from the equilibrium point. Away from the equilibrium point means, yes, away from the equilibrium point means this. It is moving away from the equilibrium point. So it is unstable. So I am marking it with red. still it is, the fixed point is, still the equilibrium point is semi-stable. Still it is semi-stable equilibrium point. I hope you are understanding this. Now let us look into something more interesting. I mean, another example. Many of you might think, what happens with cubes? X dot equals to x cube. So if you take x dot equals to x cube, what happens? So how x dot x cube looks like? How x cube looks like? It will be like this, smoothly and coming back, right? So in x dot equals to x cube also, you will, what equilibrium point you will have? Equilibrium point is x dot equal to 0 or x star cube equal to 0, implying x star equal to 0. It's the same root, right? So this is an equilibrium point, right? Okay. Now can we see what happens to the points here? I mean, if you draw a tangent, it will be acute angle, less than 90 degree. So what will happen to this? It will be, derivative is positive. If derivative is positive, it should move away from the equilibrium point. So it should be like this. If it is like this, then this side will be unstable, right? Agree? Now what happens to these sides, on these sides? If you draw a tangent, what happens to the tangent? Hmm? Left side? Huh. If it is negative, so, I mean, maybe your tangent is like this. So it should be where? Converge, right? So it should be like this, right? Hmm? Okay. So, okay. Now can we look into one last example? One last example is x dot equals to minus x cube. So how it should be? So it should look like, maybe you can look, I mean, all is visualization in 1D flows. So how it should look like? Yes, everything has been negated, right? Now still 0 is an equilibrium point. Agree? Still 0 is an equilibrium point. Now I'm asking you, what happens to these points? I mean, your tangents will be, is it correct? Is the graph correct? You can check Desmos. You can check Desmos also. Okay. I mean, I hope the graph is correct. Okay. So I think we drew maybe wrong direction of derivative. So how can we recognize the direction of derivative? That's my question. At this point, suppose, that means at a negative x, right? What should be the derivative? Derivative is minus 3x square, right? So f prime at some negative value 3 will be minus 3 times 9. That is minus 27, right? So derivative should be negative. That means slope should be negative. Agree? Slope should be negative. So if slope should be negative, it should be converging, right? Agree? Take any point here, f prime at positive x. That means f prime of 3, suppose. Then it will be minus 3 times again 9, right? It is minus 27 again. So again it is converging, right? Agree? So both sides it is converging. Both sides it is converging. So that means it is fully stable. Agree to this? Agree to this? I think here also we made one mistake, maybe. So whenever you are confused about the direction, so what you can do is, maybe here it's negative x, right? So say f prime at minus 3. So it will be minus 3 cube. So it will be 27, minus 27, right? So it is correct. You see that, right? So you can take any one point and check. It should follow the same. Why? Because if at one point the derivative is negative, at a nearby point, it won't change the sign unless it crosses the 0 point. Okay, so that's how you can check. Okay, very intuitive. So you can see all the cases here. In all the 4 cases, f prime x is equal to 0. F prime x star is equal to 0 where linearization fails. And you can see that x dot equal to minus x square and x square have semi-stable equilibrium points, whereas x dot is minus x cube. Is this direction also fine, right? It is also semi-stable, right? But when you consider x dot equal to minus x cube, the equilibrium point is stable. It is not semi-stable. So you can see, I mean, how nicely you can analyze this 1D flows. As opposed to 1D maps, 1D flows require more visualization insights. Okay, through visualization, you can understand a lot of things. Okay, now let us go to an example. I mean, a ecological example. An ecological example that is the same thing as logistic growth. So, logistic growth. I mean, if you want to understand the population dynamics, that's how logistic map was. Xn plus 1 is r xn into 1 minus xn. Similarly, the same model has a ODE counterpart. That means a flow counterpart. Okay. So what's the counterpart of this? It's the same. X dot equals to r into x into 1 minus x by k. So r and k are the biological parameters here. So here r and k are biological parameters. They are the biological parameters. Okay. Now my question to you is, this is a 1D flow, right? Is it a 1D flow? It's a 1D flow. X dot equals to r into x into 1 minus x by k. Now my question is, what are the equilibrium point of this model? For this model, what are the equilibrium points? Yes. What should I do? First step. What's the first step? Yes. You should be more vocal. I mean, else how will you understand? So x dot equal to 0. X dot equal to 0. What is x dot? No, what is x dot? X dot is given as r into x into 1 minus x by k equal to 0. Yeah, that that is already given to you. So therefore, you just set it to 0. So what solution you get? You will get two solutions. One is x star equal to 0 and x star equals to k. Agree? X star equal to 0 and x star equal to k. Now, after you find this equilibrium point, what is your next step? Determine their stability, whether they are stable equilibrium point or the unstable equilibrium point, isn't it? So determine stability. Determine stability of the equilibrium point. Exactly, right? So can you say this is x dot equals to f of x, right? What is f of x? F of x is nothing but r into x into 1 minus x by k, right? So what is f prime of x? That is a derivative. That is a derivative. What is a derivative? Can you differentiate it? R minus 2 r x by k, isn't it? Means you have to do, else how will you get? Agree to this or no? What is f of x? R into x minus r x square by k. Agree? Agree, right? If you take the derivative, what will happen to this term? It will be r. What will happen to this term? R minus r by k is constant. X square differentiation will be just 2x, right? Agree. So the same I have written here. Agree, right? So now to determine stability, what you have to do? F prime of x star. Check the sign, right? Let us say this one is x1 star, this one is x2 star, two different fixed points. So what happens to f prime at x1 star? That means f prime at 0. So what you will put? You will put just 0. If you put 0 in this equation star, what you will get? R. You will get R, right? Isn't it? If you put x star equal to 0, you will just get R. So now x1 star is stable when f prime of x1 star is derivative is hmm? Yeah, but derivative should we found it out, right? Derivative should be less than 0, isn't it? For that, derivative has to be less than 0. That means r has to be less than 0. Derivative is nothing but r. Yes. Now x1 star is unstable when f prime of x1 star is greater than 0. Derivative is positive. It is unstable. So it is r is greater than 0. X dot is derivative and that is equal to f of x. And that derivative will decide stability. Huh. F prime x. But x dot is f of x. Okay, I will clarify the story again. So equilibrium point, what is equilibrium point again? X star such that f of x star equal to 0, right? We have the flow x dot equal to f of x, right? Now, second, x star is stable, fixed equilibrium point x star is stable if f prime at x star is less than 0. F prime at x star. Remember x dot equal to f of x, but you are taking derivative of f. Hope that is clear, right? That's the plan, right? Okay. So can you see here, like same thing, but here it is less than 1, but here it is less than 0. So that's the difference you are seeing in between maps and flows. So in maps, it was less than 1 and it is stable. Here in ODE, like flow, it is less than 0 for stable. And for unstable, you need f prime of x star is greater than 0. So you can see the difference between the 1D map and a 1D flow here, right? Okay, fine. Now, can we determine stability of x2 star? What happened to x2 star? So for x2 star, what is x2 star? x2 star is equal to, what is x2 star? It is written on the board. I will draw it for you very nicely. No, I will draw it for you. Can you see here? Okay, yes. You have to be more attentive. Whatever is written on the board, you have to check. So x2 star is k. So what is derivative of x2 star? That is f prime at k, right? What is it? Can you substitute here? F prime k. What you get? R minus, yes, minus r. It is minus r, right? F prime of k is minus r. So x2 star, then can we interpret stability? X2 star is stable when f prime of x2 is less than 0, right? F prime of x2 is less than 0. Now, x2 star is less than 0. What is f prime of x2 star? Nothing but f prime of k should be less than 0, right? When it is less than 0, when minus r is less than 0. Minus r less than 0 means r is greater than 0. So x2 star is stable when r is greater than 0. And x2 star is unstable when r is less than 0, right? Can you see the, what you call, let me draw here. See, x1 star has been stable when f prime is less than 0 or r is less than 0. X1 star is stable when r less than 0. But x2 star is unstable when r less than 0, right? So what you can see from here? You can see from here that x2 star, okay, if r less than 0, then x1 star is stable and x2 star unstable. And when r is greater than 0, it happens the opposite. That means x1 star is unstable and x2 star stable. Okay, is it okay? Right. So what I will ask you. Hmm, okay. So you can see clearly that this is the case. So what I ask you now is, can you draw this in Desmos? Can you draw this in Desmos? Yes, just this function. I mean, this function here. Okay. Just let me know where it intersects. So just let me know where it intersects and convince yourself that yes, exactly, you see 0 and k. You see 0 and k as the equilibrium points. Okay. Are you able to see something like this? Like maybe I can draw it here again. So hmm, agree. So you might see something like this. Like, why I'm not able to draw. Hmm. Yes. So you will see something like that. Um, you might see, okay, where it is intersecting, can you check? That's what we want to know, where it is intersecting. I mean, it is something like this. I mean, here it is x dot and here it is x. It will be something like this, right? So here you will see x star equal to 0, x1 star, and x2 star is k, right? So this is how graphically also you can check what are the equilibrium points. Okay. Yes, intersecting. So what does it mean? Y-axis is x dot. That's what you are plotting, right? Y-axis is that. So if it intersects here, what does it mean at this point? X dot equal to 0. The y-axis is 0, right? You agree to that, right? Okay. So fine. So that's the idea behind it. Okay. So one more thing is about the existence of this solution. When the solutions can exist. Okay. So say like you have x dot equals to f of x, and this is a 1D flow. Okay, 1D flow. So the idea now is, can you check when the solutions can exist and be unique? So this is known as existence and uniqueness. Existence and uniqueness. Okay. So the idea is simple. That is solutions. So the solutions to this flow, solutions to 1D flow, um, x dot equals to f of x, right, exist and are unique if f of x and the derivative f prime of x, okay, are both continuous, are continuous and differentiable respectively. Okay. If that this happens, if this happens, then only your solutions to the 1D flow will exist and will be unique. Okay. So you can just tell whether your f of x is continuous or not. How will you how to tell f of x is continuous? So you might remember your class 12th NCERT definition. So f of x will be a continuous function. When it how it is continuous? So it will be something like this. You can draw without lifting your pen up. That's a continuous. No, if you can draw the function without lifting your pen. I mean, can you draw this function without lifting your pen? No. Here you can draw, then you have to lift the pen and draw here. So this is not continuous. Whereas this is continuous. Okay. Agree. Now f prime x has to be differentiable. What does it mean? It means it should not have any sharp points. That means it should not look like this. Why? Because here it is a sharp kink. So this is a sharp kink. And a sharp kink means derivative cannot exist. I hope we remember this from our numerical method course. Yes, you can have multiple, slopes. You can have multiple slopes. Okay. So derivative cannot exist. Yes. So this is non-differentiable. Non-differentiable. Okay. Whereas this is differentiable because it's very smooth. You can have a tangent. So this is differentiable. So you have seen now where function can be differentiable, non-differentiable, and where it can be continuous and not continuous. Okay. So that's the plan. Okay. So similarly, you cannot have any oscillations. You cannot have any oscillations in 1D flows. So consider a 1D flow that is x dot equals to f of x. Okay. It is known as a 1D flow, and you cannot have oscillations here. You cannot have oscillations. Why you cannot have oscillations? Because we know that it has only room for one dimension. That means it can either go as positive x or negative x. It can be either positive x or negative x, right? So it doesn't have any room for your oscillations like this. It can either go this way or that way. So what are the now that we have understood about 1D flow, now my question is what kind of dynamics? What kind of dynamics? What kind of dynamics can the 1D flow that is x dot equals to f of x can exhibit? Okay, that's my question. What it can do you think? See, it can either approach an equilibrium point, right? Approach an equilibrium point, then it means it is stable equilibrium point, right? Second thing it can do is diverge away from the equilibrium point. Diverge away, okay, from equilibrium point, and that is unstable. So diverge means it will go to infinity. Okay. Third point, what it can be do? Anything else? That means it is approaching an equilibrium point. Same case, right? Okay, so no other case possible. No other case is there. Okay, it cannot oscillate. It cannot exhibit chaotic dynamics also. So these are the only two things a 1D flow can exhibit. Okay. Okay. So what we can do is, let us see. Uh, okay. So let us see now the bifurcations. Okay. So what are the bifurcations in 1D flows? Bifurcations in 1D flows. Okay. So the idea is simple. Okay. The idea is simple. That is, what is a bifurcation? Last time we understood that if you put a weight and that is supported by an iron rod, okay, and it is in the ground, right? What happens? This is suppose 10 kg. Now the same thing, you increase the weight, another 20 kg. Then if you will see after adding the 20 kg block, what will happen is it will start tumbling, right? It will start tumbling. Add more, maybe 1 kg. Okay. After adding 1 more kg, what will happen is it will break. It will break. Okay, it breaks. So what you saw when you increase the weight from 30 kg to 31 kg, it broke, right? So you can see that 31 kg is the maximum weight. I mean, it's the tolerance weight, tolerance. It after this weight it will break. So such kind of parameter at which the behavior, this behavior changed, right? Suddenly the metal broke, the behavior changed. So the weight or the parameter at which the qualitative behavior of the system changes is known as a bifurcation. Okay, is known as a bifurcation. So that's we were increasing the weight. We were increasing the weight, right? So what is weight? Weight is referred to as a parameter. Weight is referred to as a parameter, right? Here. Okay. So the definition of bifurcation is as follows. Okay, the definition of bifurcation is as follows. So the idea is, as a parameter changes, as a parameter changes, the qualitative, the qualitative behavior, the qualitative behavior of the vector field, or we say it is a flow, right? Changes dramatically, changes dramatically. That is dramatical, right? Because the beam was there, then suddenly it broke. That was a dramatic change. So as the parameter changes or as the weight changes, the qualitative behavior of the flow changes dramatically, then it is referred to as bifurcation. Such a phenomena is referred to as a bifurcation. Okay. Now, there are many kind of bifurcation exhibited by 1D flows, even though what they can do is they can stay at one point or diverge. These two things only they do, but even though due to these two things, they show a lot of bifurcations. Okay. So what are those bifurcations? So same as 1D maps, like let us go to our comparison table, same as 1D maps, heard, same as 1D maps also, same as 1D flow also show bifurcation. Okay, also show bifurcations. And what are those bifurcations? Those bifurcations are saddle node bifurcation. Okay, those bifurcations are saddle node bifurcation, period doubling bifurcation, sorry, transcritical bifurcations, pitchfork bifurcation. Okay, so